the effect, the two-stage least squares estimate is minus 0.012 on the labor force participation probability, where other income is measured in thousands of dollars. Okay? If you use the Rivers-Wong approach, you get minus 0.011. So you would hardly say that somehow two-stage least squares is leading you astray in that case. And in fact, now that's the averaged effect, of course. So if you looked at extreme, if you put in more extreme values of the income variable, then you should see differences. But in terms of getting the average effect, once again, the linear model seems to do pretty well with that. And in fact, that turns out to be the case also. That I do have an example. I didn't write it down for exactly the case where you do a linear probability in each stage. And in fact, that does raise an important, I mentioned this before, but I'll say it again. The lack of procedures that are short of just saying do full maximum likelihood when you have discreteness in Y1 and Y2, I think helps to explain why people are just doing these linear models and saying, evidence shows that this gives a pretty good estimate of the average effect in lots of cases. Okay, not always, of course. It might just be estimating the effect of the compliers, for example, but certainly when you compare nonlinear procedures like the Rivers-Wong with these things that are based on just linear models, you often find this close association in the estimates. Okay, so as I was saying, when we turn to multinomial responses, because multinomial probit gets difficult to estimate with many alternatives, although Hito will be talking about that a little bit day after tomorrow, I guess. Still, clearly, the simplest way to go is to use things like logit and nested logit. The problem with trying to account for endogeneity in those models is that the normal distribution doesn't mix very well with the logistic distribution. And so even if you start with an equation like 28, which I've now written y2 to be a vector, as long as everything is normally distributed, you don't really have to worry about having one or more of them. The problem is if you write down 28 and you start with a structural model, which is a multinomial logit, conditional on some unobserved thing, and then you try to derive the estimating equation based on that, you get a mess, basically. So there are some who are proposing to, and I think partly this is influenced by this recent literature on average structural functions and so on, is basically they're saying, well, look, whatever you start with in the structural model is pretty much arbitrary anyway, so why don't you just do something which is simple once you get to the thing you can actually estimate, which is, in this particular case, would be to model that probability that's 2 lines below 28 directly. So in other words, once you have established that you can actually identify the objects of interest from that probability, then you can think about it as just choosing a sensible approximation to that probability, where in the end the V2s are going to have to be integrated out, averaged out, in order to get the partial effects. But that's very easy if, say, you specify a multinomial logit or a nested logit at that particular stage. Now, whether this is going to catch on or not, I don't know, but there's a paper by Petrin and Train, for example, that does this. And actually, they compare it with the Berry, Levinson, and Pecos approach and actually get very similar estimates, and that'll be talked about tomorrow as well. So I don't know if this is a general strategy that one should be pushing, but the point is, if we get to, when we get to the semi-parametric approaches, it's really quite in the spirit of that, except that you're saying, I'm going to use a parametric model instead of some really flexible non-parametric approach. Okay, in terms of, there are other selected cases, let me just talk about this briefly, where you can actually get somewhere with a control function approach, but again, it's fairly slim pickings when y2 is binary or discrete in general. One case is where y1 follows an exponential model, and so y1 could be a count variable, or it could be just some other non-negative variable where you're willing to assume that the mean response is an exponential form. And again, the way that this is usually done is by adding an omitted variable, r1. So this is thinking of a case where, again, you would like to control for r1, you can't, and r1 is correlated with y2. So starting from here, then because the exponential function is relatively easy to work with, right, because of its properties, that the exponential of the sum is the product of the exponentials, you can derive control function methods in this case as well. So y1 can have some discreteness. Certainly, like I said, it could be a count variable. y1 could even be something that piles up at 0 and is roughly continuous. Of course, we usually model that as some sort of Tobit type model, but there's nothing that says we have to if what we want is just a functional form that keeps the expectations to be non-negative. Okay? So there's nothing that says this equation 29 can't be applied for basically any non-negative response variable, provided we've settled on being interested in the effects on the mean response. Okay? So there are a couple of things that have been done. In the case of where y2 is a continuous variable, not surprisingly, there's a set of assumptions under which adding reduced form residuals to the exponential model and then using either nonlinear least squares or some quasi-likelihood method does produce consistent estimates. Terza worked through the case where the y2 is actually binary and follows a probit, and there is a control function that's written, again, it's the equation above equation 30 that, well, it's messy, but certainly you can see that what you have to do in a first stage is a probit, and then you have to do some sort of nonlinear estimation in a second stage. So that there are methods in the exponential case. That I think the control function methods are in the exponential case, though, they're certainly going to be efficient lots of times, or more efficient than an instrumental variables approach, but there is an IV approach that works fairly generally, and it was worked out. It's actually a very simple thing to work out once you see it by Malahi, and that is to basically just find moment restrictions that can be used in generalized method of moments. And so 32 is a set of moment conditions that generally identifies the parameters. And the important thing is it doesn't restrict the nature of y2. So y2 could be discrete, it could be continuous, it could be something else. And the only thing that needs to be assumed basically is independence between the omitted variable r1 and the instruments. Okay, but that's much weaker than imposing reduced form restrictions on y2, okay, which in general is, if we have a continuous variable or binary, we might be willing to do that, but there's no reason to do it, and this certainly works more generally. Okay, so I should at least talk about the semi-parametric and non-parametric approaches also. So let's just return to the binary response case and see what it is that has been learned here. If you write down the equation again as y1 is an indicator function, then the question is where y2 is actually inside x1, and it could be in there in basically any way, but maybe just think of it as showing up additively. Then Blundell and Powell have this paper where they showed how to estimate the so-called average structural function when y2 takes on, has a reduced form given a few lines down. Actually, I guess I could use this right there, where G2 is actually unspecified. Okay, so you don't have to have a linear reduced form or even any parametric function. You have to have this additive structure, though. So they consider the case where you have this additive, this reduced form with an additive error that is independent of the z's. Okay, so if you're hoping that this somehow is going to apply to the case where y2 is discrete, it doesn't. Okay, because again, no matter what you choose G2 to be, tacking on an additive error and then saying it's independent of Z is imposing real restrictions that basically don't hold when we have discrete responses. Okay. But if you do assume that, in fact, basically you assume jointly that U1 and V2 are independent of Z, then it turns out you can estimate the parameters up to scale, and you can actually estimate the distribution function for U1. They show how to do that. And so you can estimate both parameters, and you can estimate the averaged effects, the partial effects. So it's nice because you can get estimates of both things, and you don't have to make a distributional assumption for U1. You don't have to make a distributional assumption for V2. But it doesn't help when Y2 is discrete. So that's why I said the cases where we really don't have anything else, we still don't have anything else except maximum likelihood. Okay. You can go even further with this and not put parameters in at all. So if you just write, let's see, I haven't, oh, oops. Yeah, if you look at this equation here, you can start off with an equation like that where y1 is some unknown function of the exogenous variables, the endogenous variables, and then this unobservable u1. If you still maintain this additive structure as in 36, then you can estimate the average structural function very generally, which means you can compute partial effects. So no functional forms are here anywhere, but you still have this assumption. So even though the u1 can appear in a nonlinear function in affecting y1, it's not allowed to appear, the reduced form errors here have to appear additively and be independent. So again, this certainly can give you an analysis that's more flexible than, say, doing a probit or the Rivers-Wong approach, but it doesn't get at the issue of discreteness in Y2. Okay. So remember, I mentioned this movement by people who are trying to come up with simple estimates in these cases. The fact that you can estimate something interesting by starting here and using this, and then just estimating this function right here, it really is in some ways justified by this, the approach of then doing parametric models in the second stage is somewhat justified by this. It's just saying that instead of doing full non-parametrics in the second stage, you're going to do parametrics in the second stage. Okay, but again, I think psychologically, once we start doing a parametric model that can't be derived from an underlying structural model, we start getting queasy about that, even though as a practical matter, it's not really clear why we get so queasy, I think. Now, Imbens and Nui, so the question is, can you relax this additivity structure? Oops. There in 36. It plays a key role in the Blundell and Powell work, where it's independent. And clearly that doesn't cover all cases. Okay. Now, can you relax that assumption? It turns out you can, and in fact you can allow Y2 to be generated as in 37, as in the case considered by Imbens and Nui. Now, this allows for interactions between the unobservables E2 and Z, but it does require a strictly monotonic function. It has to be strictly monotonic as a function of E2. So this rules out, and E2 here is a scalar. So this again rules out discreteness in Y2. Unfortunately, you can't. So if Y2 followed a probit, then it's a monotone function, but it's a step function of E2. So, but nevertheless, this does relax that additivity restriction. And so far, except for adding inverse Mills ratios and so on, the control functions we've seen are residuals from a reduced form, an additive reduced form. Whether those are obtained from a linear regression or a non-parametric regression, they're just additive residuals. So the question is, are there other control functions that would fall out depending on what the framework is? And in this case, Imbens and Nui show that a control function, it's interesting, is actually to evaluate the conditional CDF of y2 given z at the data, and that enforces this conditional independence assumption that you need in order to implement the control function approach. So that's a way to allow for a general unknown function G2, but with monotonicity in the unobservable. Okay, so that pretty much is, I think, the state of affairs for control function methods for cross-sectional applications. Now, for panel data, one way to view these, the correlated random effects models that we talked about yesterday, is that those are essentially control function methods also. That what you're doing is you're adding the time averages of the covariates in the simplest case as a control for the unobserved heterogeneity. So in a way, I could have called those control function approaches, and in fact, Altanji and Matskin, I believe, do label them that way. And so it does make sense that one could combine those sorts of approaches with approaches that allow for more traditional forms of endogeneity. And so general results aren't really available, so I'll just quickly take you through how one might do this in a recent paper with Leslie Papke on essentially either you can apply this to a probit or a fractional response. But the setup here is there's unobserved heterogeneity in a panel data, and then there's a key explanatory variable that's thought to be correlated with not just the heterogeneity, but also time-varying omitted variables. Now, in a linear case, we would know exactly what to do. We would use a fixed effects IV method, so-called fixed effects two-stage least squares, because that would account for the unobserved heterogeneity by removing the unobserved effect, and then we'd have an instrument, and so we would just do linear IV estimation. In this particular case, the response variable can be binary, or actually in the particular application is a fraction. It's the fraction of students passing a test at either the school or the district level. So the idea is to, instead of using a linear model for that, seeing if some sort of nonlinear model gives you very different answers and allows you to look at effects at different points in the spending distribution. So this is the sort of example where, especially when y1 is a fraction and can take on values 0 and 1, so distributions for that, you can try to use a two-limit Tobit, but maybe you don't want to impose that much structure if you're interested in a mean effect. So basically, this is just an exercise in showing how you can take a specific example and come up with an estimating equation that allows for these features. Okay, it allows for them in a restrictive way, but if what you're going to do is just do two-stage least squares accounting for the unobserved heterogeneity, then perhaps it's useful to apply that to some method that allows for a nonlinear response. So as I said, the key is in this expectation 38. Y2 is the endogenous variable. It varies across time and across individual. It's an average spending measure, actually, in the application we did. The Z's are assumed to be strictly exogenous. The heterogeneity, so think of this as school-level heterogeneity, is CI1. And then there are these time-varying unobservables that you don't see, but maybe school administrators see. And maybe are fiddling around with spending based on the crop of students they see coming through, or there are lots of stories about why spending might be correlated with time-varying things that you don't observe, not just the so-called school fixed effect. Okay, so this setup, as I mentioned, the practice of using fixed effects two-stage least squares has become fairly common as a tool for policy analysis, and so this is supposed to be mimicking that, but allowing for a functional form that's more consistent with the response variable that we have. Okay, so this device, the Chamberlain device in 39, is one way to get started, and that's to say we don't want to assume that the exogenous variables are completely independent of the heterogeneity. The instrumental variable is what's known as a foundation allowance, which has to do with the way Michigan is funding its schools currently. I won't go into that, but it depends exactly on initial conditions of what schools were spending before the policy change. So you can't just say the school heterogeneity is completely independent of the instruments. So what can you do? Well, you could use the more general device where you allow the heterogeneity to depend on the whole time path of the instruments in an unrestricted way. As it turns out, that doesn't matter at all in this application, so I'm writing it as a linear function of the time average. And then when you plug this in, you get the equation at the bottom of page 39. And there's still an unobserved variable in there, which is RIT, but it's now the sum of two pieces. And both of these pieces now are independent of the exogenous variables. Okay, that's the key. So by doing this first step, where you replace the heterogeneity by this, we now get this leftover unobserved effect, which is now independent of everything. And so the method that works with, at least if you have a continuous y2 that you can think of as having a linear reduced form like that, is to estimate this reduced form by pooled OLS, which is the same as doing fixed effects, because I have the zi bar in there. And then there are these residuals vi2 that are going to be inserted in the second stage. So the question is, when can you make all of this work? Well, basically, when you make the assumption that all of the unobservables are normally distributed, you get an estimating equation that you can easily work with. And the estimating equation is in 43. So what happens is each time you do one of these substitutions, both to allow for the heterogeneity and then secondly for the contemporaneous endogeneity, you rescale the coefficients, right? In a linear model, this wouldn't happen. You would just be adding stuff and the coefficients of interest would be staying the same. But because of the nonlinearity, the coefficients get rescaled. Well, happily, in the end, it's exactly those scaled coefficients that you want to estimate in order to get the partial effects. So after making certainly some strong assumptions, you can get to equation 43, but now this leads immediately to a simple control function approach where you put in both the time averages and then also these reduced form residuals from the equation for y2. And since y2 is a variable, it's log of spending, it's not crazy to think of that as having this reduced form with an additive independent error. It's not completely general, of course. So again, you can estimate this very easily using two steps. You do a fixed effects regression in the first step, get the residuals, and then you do something like a pooled probit, which is generally consistent even in the fractional case, to get the scaled parameters, and then the averaged effects are given in equation 45. So this is a very straightforward procedure, and there was nothing else out there that we could use except we could do a combination of the Altanji, Matskin, and Blundell-Powell stuff. And what that would do is, in the first stage, you would do something more flexible than just linear fixed effects. And in the second stage, you would do something more flexible than just a probit response function. And in the end, you can ask whether that matters very much. In this particular application, so I'll stop after, just to give you some idea about whether this matters, the fixed effect IV estimate of the spending effect, so this is a 10% increase in average spending, increases the pass rate by 5.6 percentage points. So that's just using a linear model, of course, including aggregate time effects, controlling for poverty rates, and a couple of other things. And you get, a large average effect. Of course, it's not measured that precisely. Its standard error is about 2.2. If you do the nonlinear model, okay, as I suppose, and one way to think of it is you're imposing a lot more restrictions on the distribution of heterogeneity, and you're trading that off for a more realistic functional form for the response, and the question is, do you get very different answers? No, you get 5.8 instead of 5.6, and you get a standard error that's a little larger than you do for the linear two-stage least squares. Now, so are these kinds of nonlinear models a waste of time? Well, of course, what happens is if you look across the distribution of spending, you get different effects. And so one thing is the average effect is about 5.8, but let's see, I have this written down. If you look at the upper and lower quartiles over different years, the effect ranges from about 4.9 to 6.6. So, 5.8 is basically in the middle of that, and the question is, do you get much wider variation, of course, if you look at the lower and upper deciles, well, not much wider, you get somewhat wider variation. So then the question is, do you care about that sort of thing? And the answer is, well, it's an alternative to the linear model, and you can certainly try it. So the final comment is, this is exactly the sort of problem where this more recent work can be applied. And, I don't know, if you have 500 or so school districts, is that sort of data set up to anything more than what we did here? I don't know. Certainly simple checks of putting in quadratics and interactions didn't make any difference, and so you wonder whether doing something like allowing full non-parametrics is going to make a difference either for at least the average effect, since the linear model gives you basically what the nonlinear model does in that case. Okay, so this is a good area to keep an eye on to see what's going to happen with the case where y2 is discrete, because in this case, this hinges critically on this linear reduced form for y2 with an additive independent error, as do most of the other methods. Okay. Questions then? Yes? Yes. Well, how much do you get in terms of efficiency? Well, saying things like linear models, yeah, I should be a little careful with that, right? But it is true that if you're talking about averaged effects, it's not too surprising that a linear model often does pretty well for that. So if the idea was to say apply, let's just take this example I went through, to apply a nonlinear method to get something that's more efficient. Okay, now, a couple of things about that. We just did a pooled probit in the second stage. We didn't try to do any kind of GMM procedure or anything like that. Okay, so there may be some efficiency gains there. But the same is true when we did the linear model. We just did a pooled two-stage least squares without trying to do something more efficient than, like GMM or something like that. Well, in that case, the estimate of the average effect is actually more precise for the linear model than in the nonlinear model. So it's, in that case, you can't, really say that is an efficiency gain. In cases where you're choosing between, doing linear IV or doing the Heckman, adding the generalized residual, I don't know. I guess I don't know enough about various applications where that's been done. But you do have to correct for the estimation of the generalized residual. So that certainly is going to change the comparisons. I don't know. When you're doing instrumental variables, it's hard to eke out any additional efficiency, right? No matter what you're doing. Yes.
It seems plausible that in many circumstances, the effects of the instrument on the endogenous explanatory variable can be heterogeneous, perhaps for unobserved reasons. So, for example, in Guido's lecture yesterday, we learned that perhaps for unobserved reasons, there might be always takers or never takers,
Mm-hmm.
multipliers or even
Right.
defiers that affect how the instrument, for example, the lottery number might affect enrollment in military service.
Mm-hmm.
You mentioned a bit when you talked about in a non-parametric context that, for example, in the Inbens and Muley work, that it's possible to have some sort of interaction
Mm-hmm.
between unobserved heterogeneity and the instrument in the regression on this endogenous explanatory variable. I was wondering, in the linear context, is there a way to handle correlated random coefficients in the reduced form as well?
Yeah, that's a very good question. Certainly there should be, because if you right, the question, I think the last part of the question is to, in the reduced form, right, to allow for some sort of random coefficients, or at least some heterogeneity in how the instrument affects the endogenous explanatory variable. Certainly you could do that, and then of course the problem with applying the general methods is that you no longer have an error that's additive and independent of the instrument. So in a parametric framework, you could certainly do that. But in a non-parametric framework that relies on this independence assumption, you couldn't really do that. But you might have to, in a parametric framework, let's see, how would that work? I guess you probably would have to make some second moment assumptions in order to identify all of the terms that you need to add to the control function approach, I think. Because there's always this problem, right, that you really can't distinguish, in a linear model, distinguishing between heterogeneity in coefficients and heteroscedasticity is basically impossible, right? So if you maintain that some underlying thing is independent of your instruments, then if you make enough assumptions, you should be able to disentangle that and use it in the reduced form in getting the control functions. Yes, that's a good question.